Every single day, billions of us ask questions to a machine that, let's be honest, seems to hold all the world's knowledge. We treat it like an oracle, and it feels like magic, right? But it's not. It's one of the most complex distributed systems ever built. So how does it actually work? Well, to answer our questions, Google first has to build a library. But this is no ordinary library. We're talking about an index of over 2 times quadrillion documents. That's a 2 followed by 15 zeros. Just try to wrap your head around that. It's a truly unimaginable amount of information. So the big question is, how does it do it? How does it sift through that entire universe of information, figure out what you really mean, and then serve up the perfect answer, all in less time than it takes to blink? That's the engineering marvel we're about to break down. Okay, so before we get to the solution, we really need to understand the problem. At its very core, Google Search is this constant, high-stakes battle between 3 opposing forces. First, you have to handle the massive scale of the entire web and billions of queries every single day. At the same time, it has to be incredibly fast. We're talking milliseconds. And on top of all that, it has to keep its data consistent across a huge global network. Now here's the catch. Improving any one of these things makes the other 2 way harder. The whole system is just this beautiful masterpiece of engineering trade-offs. Let's start at the very beginning, building that library. Before Google can even think about answering a question, it has to tackle this enormous first step, discovering and somehow organizing the absolute chaos of the open web. The hero of this part of the story is Googlebot. Now, this isn't just one computer, it's a massive, planet-scale fleet of crawlers. Their entire job is to constantly travel the web, 24/7, discovering new pages and updating all the ones it already knows about. But look, this isn't some random process. It's incredibly smart. Googlebot prioritizes which pages to visit using all sorts of signals, like PageRank, which is basically a measure of a page's authority, and how often it's updated. And what's really crucial here is that it uses politeness policies to crawl sites without overwhelming their servers. It's trying to be a good internet citizen, which helps keep the whole web healthy. So once all that data is fetched, it has to be organized. Google basically builds 2 main kinds of indexes. First, you have the inverted index. Think of this like the index at the back of a textbook. It maps a keyword to every single page that contains it. This makes looking things up blazing fast. Then you have the forward index. This is more like the full text of the book itself. It's slower to search, sure, but it's absolutely essential for generating those little text snippets you see in the results and, as we'll see, for the deep AI analysis that happens later. Okay, the library is built, the books are on the shelves. Now for the moment of truth, you hit search. And that single click kicks off this frantic race against the clock, a journey that has to complete in literally less than the blink of an eye. You know, the very first thing that happens isn't searching, it's understanding. Google has to figure out what you actually want. It doesn't just look for the exact words you typed. It's going to correct your spelling, it's going to expand synonyms, so a search for lawyer also finds pages with attorney, and if your query is just way too specific, it'll actually broaden the search a bit to make sure you get something useful back. And this is where the modern kind of hybrid approach really comes in. Your query gets transformed into 2 things at once. First, a classic set of keywords for finding those exact matches. And second, something called a vector embedding. Just think of this as a long string of numbers that represents the idea or the concept behind your query, not just the words themselves. This is the magic that lets Google find relevant pages even if they don't have your exact search terms. So now, armed with both your keywords and that conceptual vector, the system just blasts the indexes. This first step is all about raw speed, grabbing a huge list of every single possible candidate. We're talking about an initial list of over 10,000 documents that might be a potential match. But obviously 10,000 results is way, way too many to analyze deeply. So a really fast first-pass ranking system kicks in. It uses hundreds of relatively cheap signals, things like PageRank and how recently the page was updated, and it instantly slashes that list down to the most promising 500 or so. But even 500 is too many for the most powerful and most expensive AI analysis. So that list gets filtered one last time, down to the absolute top contenders, maybe the best 20. And only this elite group of documents gets sent to face the final boss. Now this final stage, this is where Google's deep learning advantage really shines. This is by far the most computationally expensive part of the whole process. It's where these massive neural networks perform a profound analysis to find the single best answer for your query. So you have to be wondering, how can they possibly afford to run such a complex AI on every single search in milliseconds? Well, the secret isn't just in the software. As our source material points out, a huge part of Google's technological lead comes from designing its very own custom hardware. Meet the TPU, the Tensor Processing Unit. These are Google's custom-built AI chips. And the crucial innovation here is something they call sparse cores. It's specialized hardware designed for one job and one job only, accelerating the incredibly complex math needed for semantic search and those vector embeddings we talked about. This tight bond between their custom hardware and their software, that's their secret weapon for speed. They also use some really clever software tricks to speed things up even more. With a technique called model distillation, they train a giant, super smart teacher AI, and then they use it to teach a much smaller, much faster student AI that can actually handle live search traffic. They also use something called quantization, which is kind of like using less precise numbers for the AI's calculations. It's a smart trade-off that can give you a massive speed boost with almost no loss in quality. Okay, so all of this, the crawling, the indexing, the ranking, all of it is running on top of a global infrastructure of almost unimaginable scale and resilience. This is the foundation that makes everything else possible. It never, ever sleeps. So where does all this data actually live? Well, it's not on one giant hard drive. Google uses specialized systems for specialized jobs. Colossus is the deep, ultra-durable archive. Bigtable is a massively scalable database for things like the search index itself, where you need huge throughput. And then there's Spanner, which acts as the global source of truth, a database that guarantees perfect consistency for the most critical data, like the rules that govern the whole system. The key here is always using the right tool for the right job. And how do they keep this massive system from, falling over? It's a philosophy called Site Reliability Engineering, or SRE. They use tools like Borg to manage their huge fleet of computers, and another tool called Dapper to instantly find bottlenecks. But their most powerful tool might just be an idea: error budgets. This is basically a rule that says if a service becomes too unreliable, all new feature development just stops until it's fixed. For Google, reliability always comes first. So when you zoom out, you start to realize the whole system isn't just a collection of cool technologies. It's a symphony of carefully balanced trade-offs, all guided by a few core principles that make the whole thing work. We've seen these principles in action, right? Architectural segmentation, using those fast databases for most things, but perfectly consistent ones for the really critical rules. ML acceleration, building custom chips like TPUs to create an unbeatable advantage in AI. And finally, a constant feedback loop, where insights from the ranking process are used to make the initial web crawling even smarter. It's a system that is always learning and always improving itself. And that brings us to a final, bigger thought. We started by calling it a library. But this shift from simple keywords to true semantic understanding, it's changed everything. Google Search is evolving into something way more powerful. It's becoming a library that doesn't just store information, but is beginning to truly understand it. And that, fundamentally, changes the very nature of what it means to ask a question.